So fundamental techniques for design and analysis of algorithms. And what we already did, number one, divide and conquer. Divide and conquer. This is, the idea is very simple. Just we are given a problem, then we try to reduce the size of the program from n to something n over 2. Okay, so size n, size n program, we have a two size n over 2. Okay, so we solve these smaller problems independently, then we combine the result to get the final result, final answer. Okay, that's the divide and conquer. Very nice technique. And then our second technique is DP, dynamic programming. Dynamic programming. Okay, what is the idea of dynamic DP? That is also quite simple. We just try to do exhaustive search. So this is very fundamental. This is a very naive approach. We just try to find the answer by using the whole search. Okay, by using tree structure. Okay, so we have a lot of nodes. That is something like 2 to the n. Okay, because we have n items, and this is a binary tree. So the whole nodes would be 2 to the n, a huge number. Huge number. But if you take careful look, then it turns out, for example, this level, a lot of nodes. But you notice that there are many nodes of the same value. So this node and this node is the same, and this node is the same, and this node is the same. Okay. So we have a lot of same nodes. That means you can merge, you can combine those same nodes into one node. So that is a basic idea of dynamic programming. Then you can reduce the size of the search space from 2 to the n to something like polynomial, n square or n cube. That is a very nice technique. Okay? So I'll show you today. I'll show you another example. Example, I don't know, number 5 maybe. It's a matrix. Okay, so this is a very standard example for explaining dynamic programming. This is a matrix multiplication. So we are given, for example, 3 matrices, A1, A2, A3, and we like to multiply all 3 matrices. Okay, and A1 is has a size of 10 by 30, and A2 30 by 5, and A3 5 by 10. This is the size of the matrices. And that means A1 looks like this. And A2 And A3 looks like this. We just wanna multiply those three matrices. Okay. We have two different ways. Matrix multiplication has, for matrix multiplication, distributive law holds. So we have two ways. Number one is we multiply A1 and A2 first, then A3. And number two is we first multiply A2, A3, and then A1. Okay? So distributive law follows. We can get the same answer. Okay? It's the same answer, but the amount of work is just surprisingly different. I'll show you that. The two things. Okay. Number one, what about multiplying A1 and A2 first, then A3? Okay. For first multiplication, A1, A2, okay. Just remember matrix multiplication. So we multiply A1 and A2, then the answer is something like this. Yes. No. Okay. The resulting matrix is 10 by 5. What is the value of this entry? This entry, that is multiplication this number and this number. Okay. So we have add this number and this number. Then no multiply this number and this number and this number and this number. Then we take sum of all those values. Okay. Then you can get this value, right? Okay. So the number of work is okay. We have 10 times 5 numbers, and to get each number we need 30 multiplications. So this is a number of work. It's the amount of work. That is a number of arithmetic computations, roughly speaking. Okay, roughly speaking. But I'll change a little bit. This is the same as 10 times 30 times 5, of course. But I want to use this order because this is easy to consider. Because this 10 times 30 times 5 means, okay, we are now multiplying this guy and this guy. Then this is the side 10, 30, 35. Okay, that means, but number of operations 10, 35. Okay? So 10 by 30, 10 multiply 30 multiplied by 5. But this is the number of operations. Okay, so I'll use this notation. So 10 times 30 times 5 is equal to what? It's equal to 1500. And then next, we multiply this guy and this guy. How many operations? That is 10 times 5 times 10. 10 times 5 times 10 is equal to 500. In total, we need 2,000 operations. So this is the work we need to do this multiplication. Okay. Now, what about the second case? Number 2. Okay. For multiplying A2, A3, A2. This is not a good position. Okay, that's fine. So if we multiply those two matrices, then we get 30 by 10. Oops. Yes. We get a pretty big matrix. 30, 10. Okay. So, number 2 approach for A2, A3 multiplication, we need 30 times 5 times 10 is equal to what? Yes. 1500. Then next. I will need to multiply this guy and this guy, right? This guy and this guy, this guy and this guy, then this is pretty big. 10 times 30 times 10. 10 times 30 times 10 is equal to 3,000. The total amount of work is 4,500. Oh, yeah. You know, it's more than twice. That's more than twice compared to this one. So you know that this number 1 approach, this order of multiplication is much, much better than the second one. And that's why it's very important to obtain, to find the best order of multiplication. Okay? Any order of multiplication is okay. You can get the same answer. But the total amount of work is very, very different from order to order. It's really important. Good. This is pretty simple because we are given only 3 matrices. What about we are given, for example, 5 matrices? Okay, now we are given A1, A2, A3, A4, A5. Okay. In the case of the 3 matrices, we have only two different orders. How many orders do we have now? How many orders of different multiplication? Well, okay, maybe we can do A1, A2 first, then A3, then A4, then A5. This is one order. This is one order. Or maybe okay, A1, A2, A3, A4, A5. This is another order. Maybe A1, A2, A3, A4, A5. This is another order. Many, many more. Many, many more. Okay. So how many different orders? How many different orders? Actually, it's many. It's really many. Maybe it's if I have time today, I'll show you how many different orders. But it's approximately 4 to the n. Different possibilities. I'll show you why 4 to the n at the end of this class, if I have time. If I don't have time, then I'll skip. Okay? But anyway, we have a huge number of different orders. What then if you are given n matrices? Really big number. Okay? So your task is to find the best order, among these 4 to the n different orders. Wow, it's impossible. 4 to the n is just too much. Okay? Then what we do is just dp. Just dp. Okay? dp means what? dp is simple. Just we try to find the best order by exhaustive search. Exhaustive search. What would be exhaustive search this time? Oh, it's pretty easy. Exhaustive search. Okay. What would be our exhaustive search this time? Okay, this is our final goal. Multiplication A1 through A5. Okay. What is the last multiplication? What is the last multiplication? We have 4 possibilities. Okay. The first possibility is A1 and A2, A5. So this is the last multiplication. Okay, we first multiply A2 to A5, then the last time we multiply A1. So this is one possibility. The second possibility is 1, 2, and 3, 5. Okay? So that means we multiply A1 to A2, and we multiply A3 through A5. Then finally, we multiply those 3 things. So this is the second possibility. The third possibility is, of course, okay. So this is 4 different possibilities or last multiplication. Final multiplication. Okay. Final multiplication. Then the second last multiplication. For example, in this case, we have 3 possibilities here. So A2 and 3, 5, and 2, 3, 4, 5, and we need more space. And 2, 4, and 5. Okay? So we have 3 possibilities. And for this, 1 and 2 is, of course, only one. There is no choice. 1 and 2 just multiply. Okay, but in this case, we have 2 possibilities. 3, 4, 5, and 3 and 4 and 5. Okay? And this is also 2 possibilities. 1, 2, 3, and 1, 2, 3. And of course, more. Then this is again 2 possibilities, and so on and so forth. So this is a search tree, exhaustive search tree in this time. Okay. What would you find? What would you figure out? Again, We have many, many same things. Okay, so suppose that you have completed this search tree, then you can get the final answer, the best order, by computing the work of each multiplication. Okay? So for example, you know that you know that to multiply 2 and 3, the amount of work is something like 50. Okay? And 2 and 4, this again 2 possibilities. So again, you can get some you know, 25 and 70, and then this 2 to 4 is maybe, I don't know, 115, and so on and so forth. So you can get those, you know, from the bottom to the top. So you can select the best order, like this. So you can complete this search tree. Then you can obtain the best order. Okay. Now, no, the idea of DP comes in. Look at this. Look at this. You know, the amount of operation to multiply 3 to 5. Oh, the same things here. Okay? So once you know that the best way of multiplying 3 to 5 is, I don't know, this one, and then this is maybe 153 operations, then, you know, this is of course 153. You don't have to, you know, calculate the same thing twice. Okay? If you once get the best order here, then of course you don't have to do the same thing again. Okay? So that is the idea of a DP. Okay. So, okay, so this tree could be huge. Could be huge, but the number of intermediate matrices like this and like this and like this, the number of intermediate matrices is only n squares. Okay, just n squared, because the intermediate matrices means something like this, A2 to A5. So the first matrix selection of first matrix is something like n, and the selection of the last matrix is also n. So n by n possibilities. Only n times n possibilities. It's a small number. You know, the size of the search tree is huge, but actually, you know, the appearing submatrices, number of different submatrices is very small, just n squared. That means so we are done. If okay. so just, we have only n squared intermediate matrices. So we are done. If we can find the best order of computing all of them, all of n squared submatrices. Not submatrices, I'm sorry. It's partial multiplications. Right? Okay, so then in order to do this, we usually use the following table. And the table exactly looks like what you see in the standard textbooks explaining dynamic programming. So when you see explanations of a dynamic DP, then you usually come across this kind of table. I'll show you this table in a moment. Okay. Okay, the table is a little bit this one. Okay, so this example is very small. We have 5 matrices. Each matrix is quite small. Then the table looks like this. Okay. The first row is length 2. And the secondary length 3. What do I mean by length 2? Length 2 means this entry, we write this entry, the number of operations to multiply A1 and A2. Length 2 means we need how many operations do we need for multiplying length 2 matrices, starting from A1. Okay. So starting from A1, okay, we need to multiply 2 matrices A1. That means A1 and A2. How many operations? 3 times 5 times 2. So this is 1, 2. Multiply 1, 2. That is 3 times 5 times 2 is equal to 30. This is 30 operation. Okay. Now the same thing. In order to multiply A2 and A3, we need 40 operations. 5 times 2 times 4. 3, 4. We need 48. And for 5, we need 72. For 5, 4 times 6 times 3. Okay? So we're done with length 2. Now we are going to length 3. Length 3 means, we want to multiply 3 matrices, starting from A1, that is A1, A2, A3. But now we have 2 different orders, right? A1, A2, A3, we have 2 different orders. So the first order is 1, 2, and 3. The second order is 1 and 2, 3. Okay? How many operations do we need for this? For this. That is, for 1, 2, for multiply 1, 2, we need 30. Okay? We have here, right? Plus what? So if you multiply 1, 2, then the resulting matrix is 3 by 2. So that is in order to multiply 3, we need 3 times 2 times 4. How much is that? 24. Is equal to, yes, this is 54. Is this clear? Okay? Now this. In order to multiply 2 and 3, you already have answer, 40. Okay. So the idea is when constructing this table, you can use the previous data. You can use the previous data efficiently. Okay? That is the idea. So in order to multiply 2 and 3, we already have answer. That is 40. Plus, I don't know, 60 is equal to 100. Why 60? Because in the 2 and 3, we have a 5 by 4 matrix. So the 3 times 5 times 4 is equal to 60. The sum is 100. Okay? But now, this is better. Okay? This is better. So this order is better than this. So the complexity for multiplying A1 through A3 is 54. Right? Okay. Let's do the same thing. Okay. Now you completed the second row. Now we are going to the third row. Length 4. Now we have 3 different possibilities. Okay. Now, how can I get this answer? Okay. In order to multiply 2 to 4, okay, 2 to 4, yeah. We have answer here. In order to multiply 2 to 4, the best way is here. Okay, 108. This is a complexity. So this is 108 plus what? If you multiply 2 to 4, then the resulting matrix is a 5 by 6. 5 by 6. So in order to multiply A1, we have 3 times 5 times 6 is equal to what? 90. Is equal to 198. Okay. Now what about this? In order to multiply 1 and 2, we have 30. Plus, in order to multiply 3 and 4, we have 48. Here, plus, multiply these two matrices, we have 36. Is equal to 114. Okay. And what about this? In order to multiply 1, 3, we have answer here. So here. Okay, so the 54 plus 72 is equal to, I don't know, 126. And again, the best one is this. Just the same thing. Now, we come here. Rank 5. Rank 5 is the whole thing. The whole thing. I need more space. So okay. So just we're going to calculate the total amount of operations for multiplying this order, this order, this order, and this order. Okay. But again, just notice that, just, in order to multiply 2, 3, 5, you already have answer. Where? Here. Okay. 2 through 5, we have answer here. So 1 to 14. Plus, I don't know, 45 is equal to 159. Again, here, okay, in order to multiply 1 and 2, we have answer here. Plus 3 to 5, where? 3 to 5 here, 84. Plus, what? 18 is equal to 132. Here, 54 plus 72 plus 36 is equal to too many. 114 plus 48 is equal to 152. Okay. So the best one is here. The best one is here. Okay. After completing this table, then what can get the best order? What can get the best order? Okay. The best order is this. Okay, the best order is this. The best order is that best order is this. That means the final multiplication should be this guy and this guy. Okay? The final multiplication should be 1, 3, and no. 1, 2, and 3, 5. Also 1, 1, 2, this is only two matrices, so we don't have any choice. But we do have a choice for 3 to 5. What's the best one for 3 to 5? Just look at the 3 to 5 here. No, 3 to 5 here. Okay? Then what is the best one? That is this one, the best one. Yeah, this is the best order. That means the best order is 1, 2, 3, 4, 5. Okay. So this is the best order of multiplication of those 5 matrices. Okay. Here we are done. We are done. What's the complexity? What's the complexity? Well, the complexity is something like order n cube. Something like order n cube. Why? Because the size of this table is n squared. Because we have n matrices, and n ranks. The size of this matrix is something like n squared. And in order to calculate these things, we have n different possibilities at most. N different possibilities at most. So maybe a little bit more, but roughly speaking, we need linear, we need linear operations in order to calculate each entry. So in total, we need something like n cube. Something like n cube. Maybe this might be a little bit optimistic, but not that big different. Not that big different. Okay, good. So this is a standard example, a very famous example explaining DP, dynamic programming. Okay, so we are done about dynamic programming, and then let's go to the third technique. So do you have any questions so far? So far, okay? Good. Then let's move on. Number 3, third technique is backtrack. Backtrack and local search. Okay. Today, I'm not going to this approach deeply. Today, I'll give you some idea of exponential speed up. Okay, this is a very important notion. So I'll give you the idea of exponential speed up today. And the most standard approach to get it is backtrack and local search. So I'll show you this technique next week. So today, I'll show you what this exponential speed ups mean. Okay? So, I'm going to use an example. Example 6. That is the same as before. This is equal partition. Equal partition. So we revisit. We consider this problem again. Just remember, we are given I1, I2 through IN and numbers. And we want to have a subset. We want to find the subset S. Such that the sum is equal to n over 2. Do you remember this problem? We are given n numbers, and we want to find the subset S such that the sum of this subset is exactly 1/2 of the total sum. Right? So this is a equal partition problem. However, this time we have a big difference. That means no restriction for the numbers. No restriction for the numbers. Previously, we did have a restriction for each number. Do you remember? Just look back at your note. Then you can find that our restriction, previous restriction, is that each ij is at most 100. Right? This time, we have no such restrictions. For each number can be big, unlimitedly large. Okay? Now, so exhaustive search. We again try exhaustive search, but this time just remember what we did before. So if exhaustive search is root, then the first choice is whether I1 is in subset S, in S or not. Then the sum is equal to 0, the sum is equal to I1. Then I2 okay. So this is the previous exhaustive search. And then, if you look at some level, then you have lots of nodes. Lot of nodes. But previously, since we have a restriction that each number is at most 100, then the possible different values here is very small. Okay, that means we have many same nodes. That means we can reduce the size of the search tree. But this time we don't have any restriction about the value of these numbers. These values may be all different. That means we can't reduce the size of the search tree. Wow. Okay. So we may need to check all the possibilities, all the search trees. That means we need to check 2 to the n possibilities. This is pretty bad. This is pretty bad. So this is important. Now, no DP. We can't use dynamic programming because of this. Okay, and you already know that we can't use divide and conquer either. That means we have no way. We have no idea about how to reduce this complexity significantly. Okay. Now, I'll show you the following simple idea to reduce that complexity significantly. Okay, the idea is just try to 2 to the n to 2 to the n over 2. That is our goal. That is our goal. That is what we call exponential speed up. That means, for example, if we have n numbers, we have 100 numbers, there's something like 2 to the 100 to 2 to the 50. Okay, this is still a big number, But if you compare this number to 2 to the 100, then this is much better. Okay, this is smaller than this value by a factor of 2 to the 50. It's not a 2 to, it's not a factor of 2. Now some some high school student just thinking this number is 1/2 this number. No. Okay? Please don't make such a stupid mistake. This number is not a half of that. This is a smaller by a factor of 2 to the 50. Much smaller. Okay? So reducing the complexity from this to this is a kind of big deal. Okay. Can we do that? Yes, we can. Yes, we can. Okay, so this is what we do. I'll show you an example. $80, $25, $3, $62, $5, $15. It's an example. Okay, then number 1 divides the whole numbers into 2 groups, same size. So just like this. And this is this is important. Just divide this partition into two groups. Okay. Then number 2, compute all subsets. Compute all subsets. So it is okay. Okay. So we compute all the subsets in each group, like this. Then sort them. Sort them by the value, by its sum. So here, sort them, sort those numbers. $80, $25, $53 is the biggest number, biggest sum. What's the second sum? Biggest sum is 80, 53. The third one is 80, 25. And the next one is 80. The next one is a 25, 53. And so on and so forth. Yeah. And 3, 25, and 0. Okay. So sort them. Sort them in each group independently. Okay. Now, we have 2 to the n over 2, maybe 50. So 50 subsets. And we also have to the 50 subsets. Okay. So, what is your task? Your task is to find some pair, such that the sum is n over 2. Right? Right? So in this case, we do the same thing here. Then you try to find some pair, this one and that one, whose sum is n over 2. Right? That is your final answer. Okay? Clear? So this is what you'd like to do is to find this and this. And this, the sum is 2 to the, n over 2. Okay? That is your task. Once again, we have 2 to the 50 subsets here, and 2 to the 50 subsets here. Oh, I'm sorry. Important assumption. This is sorted. Large, small. Sorted. Now both groups are sorted. Large to small. Okay? And your task is to find a pair of numbers such that the sum is exactly n over 2. How can I do that? Just check every pair. Of course you can do that. But if you check all the pairs, then what would be your complexity? Complexity is 2 to the 50 times 2 to the 50 is 2 to the 100. Wow. It's completely same as before. Completely same as just a naive exhaustive search. So you can get any gain. But there's a nice way. There's a nice way to find this pair. Okay? I'll show you. Okay, what you do is look at this. I'd say this is A. And this is B. So A is the smallest number, largest number in the first group. B is the smallest number in the second group. Okay? Then you try to check that pair is your answer or not. That means you check A plus B. If that is n over 2, then you are done, of course. Right? So probably it's not. It's different from n over 2. If A plus B is less than n over 2, let's check the sum of A and B. And if it's less than n over 2, then discard B. That means this B cannot involve in the correct answer. Why? Because it is the value. I'm sorry, to discard A. Oh, sorry, discard A. I'm sorry. This is a little bit confusing. Discard A. Okay. 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 Oops. That's really, really confusing. Wait a second. Oh, discard B. I'm sorry. Discard B. Are you okay? Do you know why? Okay. This guy, the sum of this guy and this guy is not enough. We need more. We need more. But as far as we use this guy, then the other guy's value is smaller than A. That means, as far as you use this B, you can never make N over 2, right? Because if you use this one, then the other guy is the largest one, but it's still not enough. Still not enough. Then this guy is useless. Useless. Just discard. Then this list becomes smaller by 1. You do the same thing. The smallest guy and the largest guy. You do the same thing. Okay, now, if A plus B is greater than N over 2, discard A. A. So in that case, the upper list becomes smaller by 1. Okay. So by doing this simple calculation, you can reduce the size of the list by 1. This list or that list. At least one of them can become smaller by 1. That means okay. Then, of course, the list is getting smaller and smaller like this. Then you eventually get this guy Y or X. Okay? After that, then you can automatically get to the other one, to get to the other one. Yeah. What is the complexity? Complexity is so this is no. This is the complexity of making these two lists. We have 2 to the n over 2 numbers, and we need to sort them. So we need n log n. Multiplied by 2, because we do the same thing for two groups, plus what is the complexity of this procedure? That is something like 2 to the n over 2 multiplied by 2. Why? Because that, by doing one operation, you can reduce the size of the list by 1. The size of the list is 2 to the n over 2 times 2. It's the sum of the lengths of two lists. By doing one operation, you can reduce the size by 1. That means after this operation, that you can get to the answer at worst. This value is a little bit more than n 2 to the n over 2, a bit more. But this is just a polynomial. This is exponential. So this part is much more important than this. So I would say this is not completely 1/2, but almost 1/2. Yeah. Okay. So this is what we call exponential speed up. Exponential speed up. So our speed up ratio is something like 2 to the n to 2 to the n over 2. This is exponential speed up. Okay, I have 15 minutes more, so I'll show you the number of possible matrix multiplications. So if you have two matrices, of course we have only one possibility. And 3 we have 2. And we denote this order something like this: A, B, C. And this one is A, B, C, like this. And for matrices, then we have A, B, C, D, and A, B, C, D, and so on and so forth. Again, A, B, C, D is D is B, C, A, D. Okay. So we use this kind of representation. Our correspondence is, of course, obvious. Okay. So just this means AB first, then C and D. Okay. Now we have another interesting explanation, representation for this order. That is this. A, B, C. Oh, I'm sorry. Mistake. A, B, C, D, and yes. So for this order, we use this representation by using maze. So it's a mesh. You need to go from here to here. There are many different routes, but this is one route. And this route represents this order. That means you first multiply A and B, then C and D. Okay? So this is a representation. Okay? And this one, is just the same thing. A, B, C, D. Then, we first multiply B and C. So you first multiply B and C, then A and B and C. So the root looks like this. So do you understand? The idea is that it's this cross, this x is a multiplication. So you first multiply B and C, then A, and then D. This is exactly represents this order. So that means that if you are given n matrices, then you consider mesh of n by n. Each order of multiplication corresponds to the root from here to here. Something like this. Okay? So each order of multiplication just corresponds to a root from here to here. However, there's one restriction. There's one restriction. You can't get into this part. You can't get into the left upper part because that doesn't make sense. Now you can see it by yourself. It's pretty easy. Why? You can't get into this part. This is not. It's not. Okay. So the number of different orders of multiplication is equal to the number of different roots from here to here, but without entering this part. Okay. How to calculate those number of different roots? Okay, maybe this restriction is a little bit complicated, but just forget it. So let's consider the number of roots, different roots from here to here. Now you can get into this part also. Then how many numbers? How many roots do you have? Okay, that is okay. From here to here, you have n by n mesh. Then, from here to here, you need to go through two n intersections. Intersection means here. Okay. you have n points here and n points here. So n plus n intersection. But if you go, that is the same. That's the same for any route, right? So if you go like this, but you still go through n intersections. 2n intersections, I'm sorry. And in each intersection, your choice is go to your right, or up. There are only two choices. Well, that means the total possibility is, of course, okay? The total possibility is just, you have to go through 2n intersections, and each intersection, you have two choices. To go to the right or go up. That means, just 2n choose n. Among 2n intersections, n intersections, you go right. Then, of course, the remaining intersection, you have to go up. Okay? So this is all possibility. And in a simple calculation, it's almost 2 to the 2n. Well, this is something like square root of n. But you just forget. This is not so important. So almost 2 to the 2n. 2 to the 2n. Okay, wait. We forget the restrictions. You can't get into this part. So this number should be too much. Because we calculated. We have calculated. It's a kind of a bad root also. So we have to reduce. We have to reduce the number. We have to minus. We have to minus. We have to minus the number of bad roots. But it's not a big number. Just something like maybe 1/2. Why? Because just you can consider just folding this part of this. So this is bad. Okay, so this is a bad root. So this is a bad root because it's entered. It enters this part. But just you folding this paper like this, then this root changes like this. Okay? So that means you already counted this root, and you also counted this root. Okay, it's kind of doubles, only doubles, right? So the number of correct roots might be something like 1/2 of this. So it's not big deal. Just forget. Okay. The basic idea is the number of different roots is something like 2 to the 2n, and that is equal to the number of different orders of multiplication. Okay. Actually, this is a big number, really big number, and this number is quite famous. This is a Catalan number. This is a famous mathematics that is called Catalan number. So if you look up web pages, for example, then it's pretty easy to get pages explaining this Catalan number. Exactly the number of different orders for multiplication. Okay, good. So we are done. And next week, I'd like to explain how we can get this kind of exponential speed up. The typical technique is backtrack and local search. Okay, good. So see.